All right, thanks for watching and welcome to the exciting conclusion of our heat equation extravaganza. Because now we finally have all the tools we need to solve ut equals duxx with initial condition f of x. Because previously on Pion Battlestar Galactica, what we did was the following. So steps 1, 2, 3. First of all, we define what's called the Fourier transform of u, but here the Fourier transform with respect to x. So u hat kappa t is the integral from minus infinity to infinity of u of xt ei kappa x dx. And then what we did, we took the Fourier transform of both sides, used the Fourier transform miracle, which turns derivatives into algebra, and solved for u hat. So far, what we did, we found u hat kappa t is, I believe, f hat of kappa, and then e of minus d kappa squared. And at this point, we were stuck. Now, what will help us solve the heat equation is the following clever observation. If we can somehow write the right-hand side as a Fourier transform, in other words, if we can find some function h such that the right-hand side is the Fourier transform of h, so if this is h hat kappa t, then we would be done. Then u hat would be h hat, and then we find u, our solution, is this mystery function h. So really the upshot is find h of xt such that u hat of kappa t is h hat of kappa. Because then we can conclude that u equals h. By the way, this is nothing particularly new. We have done something similar with the Laplace transform. Because what was the point of the Laplace transform? Is first of all to solve for L of y, and let's say for instance the right hand side was 4s minus 11 over s squared minus 5s plus 6. And the idea was to write the right-hand side as a Laplace transform. So using partial fractions, we're able to write this, for instance, as Laplace of, I believe, 3e to the 2t plus e to the 3t. And then we're able to conclude that y is 3e to the 2t plus e to the 3t. 3e to the 2t plus e to the 3t. And we kind of want to do the same thing here, where we have u hat, that is like L of y, and want to write this as L of our solution function. Okay, now how do we proceed? So, the idea is we want to proceed in steps. Namely, we'll first write this as a Fourier transform. And you will see our h will then come naturally out of this. So, step 4. So write e of minus d kappa squared t as the hat of some function g, so for some g. And what saves us here is the magical fact that the Fourier transform of a Gaussian is still a Gaussian. So kind of this fractal property. Because recall, if you take the Fourier transform of e of minus ax squared, where a is positive, then you get something similar. Square root of pi over a e of minus, I believe, kappa squared over 4a. Kind of like how the derivative of e to the 2t is 2e to the 2t, so something similar. And it turns out this is what helps save us, because then we can solve for e of minus kappa squared over 4a and we get square root of a over pi e of minus ax squared hat. And that's perfect, because notice this tells you the Gaussian is a Fourier transform, and that's exactly what we want. We have a Gaussian, we want to write this as a Fourier transform. And so really, all we have to do is just compare those two exponents. So it all boils down to, for which constant a do we have minus kappa squared over 4a equal to minus d kappa squared t. So the idea is equate both exponents, solve for a, and then use this formula. Okay, so let's do this. Once again, this Gaussian is a Fourier transform of another Gaussian, and now we want to apply this to here. So we just need to figure out when those exponents are equal. So for which a this is true? Well, and so equate both of them. So now what we have is minus kappa squared over 4a is minus d kappa squared t. Pick your favorite kappa and cancel it out. So this cancels out, the minus cancels out, and we get 1 over 4a is dt, and then 4a is 1 over dt, and then a is 1 over 4 dt. And so now we can plug in a is 1 over 4 dt into this formula. So square root of 1 over 4 dt over pi, and then e, so half of e of minus 1 over 4 dt, and then x squared. And then we finally have our Fourier transform, so square root of 1 over 4 pi dt, and then e of minus x squared over 4 dt. In other words, this is our function g that we wanted. So let me summarize. So I believe, maybe that's not step 5. So what we found was e of minus d kappa squared t is the Fourier transform of g, where g of xt is 1 over square root of 4 pi dt, if I'm not mistaken, e of minus x squared over 4 dt. And by the way, this function is so important, we'll talk about it in the next video, that's sometimes called the heat kernel. So think kind of like the nucleus of the heat equation. Perfect. And now let's go back to our u hat. So what we found is that u hat of kappa t, remember that was f hat of kappa times e of minus d kappa squared t. However, now what we found is that this is the Fourier transform, f hat of kappa, and then g hat of kappa t. And remember, the idea is to write this as a single Fourier transform. of something capital T. Now, before we were stuck, but now what helps us is precisely the thing we were talking about in the previous video. So how can we combine the multiplication of two Fourier transforms precisely using convolution? So in other words, this is the same thing as the Fourier transform of f star g. Because once again, and I will define it soon again, what is the convolution? It's the correct way of multiplying f and g, and in fact, it is the multiplication if you think in terms of Fourier transforms. So here, all we used was f star g hat is f hat times g hat, but in reverse. Great! And now we're ready to uncover the villain. In other words, we're ready to remove the hats, because what we have is the following. So what we found is that u hat kappa t is f star g hat kappa t. And so now we can reveal our function u. So now uxt is f star g of xt, where f is our initial condition and g is the heat kernel. So we are finally arrived at the solution of the heat equation, which is the following, to summarize. So fact, the following is a solution to ut equals duxx with initial condition f of x. Namely, u is the convolution of f and g, which is, if you want, the integral from minus infinity to infinity of f of x minus y, g of yt dy, or f of y, g of x minus yt dy, doesn't matter, where, again, f is the initial condition, and g, from g of xt if you wish, is what's called the heat kernel. So it's 1 over, if I'm not mistaken, square root of 4 pi dt, and an e of minus x squared over 4 dt. And so if you want to, you can write it explicitly as f of x minus y, and then 1 over square root of 4 pi dt, e of minus y squared over 4 dt, which is very, very cool. And in the next video, we will explore this heat kernel just a little bit more, and then I will give you a cool explicit example of the heat equation. Alright, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.